they have published. So they have more than 20 years of experience in this field of display technology. So in this Brunel University and Alagappa University, and on behalf of the organizing committee, so I would like to invite the engineer Muthulingam Kumaravel. He is working in the field in the Department of Chemical Engineering, Brunel University, London, Würzburg. So on behalf of organizing committee, I invite Professor Muthulingam Kumaravel sir for giving the talk on quantum application in displays and lighting. So he is going to give an overall reviews and in the context of device oriented applications. So he is the real experienced hand in front of you, so you can have interact with you. So after his presentation, so over to you, sir.
Thank you. Thank you. Thank you. Good introduction about me, Rama, and you are fabulous teaching. You are a good teacher, actually. I'm an engineer. I just making devices only. So my name is Muthulingam Kumaravel. I am working at Brunel University. Can you see the presentation first? Can you? Rama, can you see my presentation slide?
Yes, sir. Yes, sir. We are seeing. But can you go for the next slide?
Okay, sure.
Yeah, fine. Yes, fine. Working well.
Okay. Thank you very much. Thank you. My name is Muthulingam Kumaravel. I am working Brunel University as a device engineer. I have experience in 20 years in OLED and QLED manufacturing and characterization. Yeah. So I'm going to share with my knowledge and experience in OLED QLED fabrication. So I'm going to give some introduction about display and lighting first. So this is the revolution of the display. So everybody, I think some of you know about the CRT, the cathode ray tube display. It is actually initially started in 1930, invented in 1930, then used up to 2000. I have no idea about anybody using at the moment. It's a very bulky, and also there are limitations for the size of the display. Then it moved to 1970. That's invented then the LCD, liquid crystal display. That's more thinner and a lighter one compared to that CRT display. Then it is still using, and it's moved to the OLED display, which is I'm very keen on because I started with OLED displays. So the OLED display has a lot of benefits because it can be rollable, it can be make it a curve display, and also any sizes it is possible to make. It is invented in 2010. They make a prototype television, and there are some mobile phone displays is made since 2010. It is very popular now. You can see the color difference between the LCD display and the OLED display. Then now it's a little bit. It started the quantum dots. Quantum dots is a QLED display. Actually, it is the filter being used for the LCD display, and it is in the market now. So what is the? So I'm just going to start with the comparison with the OLED and LCDs. So why we need OLEDs? The material-wise, we used a very small amount for making OLED displays compared to LCD. LCD needs 100 times more than that OLED materials. I mean the material which we need to make for the LCDs. So the material cost, because we don't need to use any color filter for the OLEDs, and LCD we need. There are few more. I mean that frame to be used, like polarizers, color filters, diffusers, and enhancement films to be used to make this LCD display. But in OLEDs, we just use the light emitting unit. It's 100 or less. The thickness is only 150 nanometer maximum, and we use the cover and the backplane. And the view angle, you can see the pictures from any side without any color changes. I'm not any sides means I'm not telling behind the screen, but even the 180 degrees you can see more clearly that from the OLED display, but in LCD is not possible. And the contrast ratio, actually, that the pixel size, it's actually 1 million is to 1, but compared to this is only 1,000 to 1. And emission is actually, it is self-emitting, that actually the self-emitting material is being used for making OLEDs. But LCD, we using the backlight, we need the backlight and also the liquid crystals. Transparency is, we can make transparent OLEDs easily, but it's LCD is not possible because we are using liquid crystals there. And power consumption is compared to LCDs, OLED is very low. So that's why we need some changes from some development we need from the LCD to saving more energy compared to LCD. So the LCDs we are using lot of frames like, polarizer, color filter glass, TFT glass. I'm using my pointer, hold on. The TFT glass, polarizer, another polarizer, and diffuser, prism seat, like and the light guide. Like there are many frame of slides to be used to make this liquid crystal display, but compared to OLEDs, we just using the 3. We need only actually the backplane and the OLED unit, the light emitting unit, and the polarizer outplate only we need to make OLED display. So this is the OLED display structure. OLED display structure we are going to be normally pixelized. Pixelized means is the red, green, blue. We make it pixelized and make the devices. I'm just going to go. This is some small structure of the OLED, but I'm going to go very clear. I mean, I'm going to expand this structure in my next teaching slot in Thursday. But this is just to where there I'm going to talk about electron transporting layer, the whole transporting layer, and the emissive layers for everything. But it's just a simple structure for the display. And this is the simple structure for the lighting. Lighting, there we can see there's a layer of red, green, blue we are using. Here we pixelized red, green, blue we are using. That is the difference for the structures we use to make this OLED display and lighting. The next, this is some pixelized devices we made at Brunel using our all-back solid-state machine. So it takes between 2 to 2.5 hours it takes to make one of the device from the preparation of the substrate. So this we use our red, green, blue prime colors, and also we could make a white color for the lighting purpose also. So I'm just going to give you some, there are different methods of to suppliers making the OLED TV. So there are some important parameters we are going to see here. So these are the two main main manufacturers of OLED TV, LG Display and the Samsung Display. They are using backplane architecture. That is the one of them which LG using indium gallium zinc oxide thin film transistors. They are using same time that Samsung using polysilicon. And these transistors different. I'm going to talk about the next my slot on Thursday. And the stack. And the stack, you can see the tandem stack they are using in LG display, and Samsung using just the single stack. The stack is a single stack means it just one anode and cathode between their whole transporting layer and emissive layer and the electron transporting layer. So there's a single unit. But when we use the tandem, we are using 2-3 single units. We just connecting with the interconnecting layers. So, and the color, the LG display using some yellow, orange, blue colors. When Samsung using the prime colors of red, green, blue. So there are some difference, and also you can see that driving voltage it becomes more than 2 times because it's a tandem. It take more current than that single one, and so the difference is the lifetime, because the lifetime will be improved when we use the tandem device. All these I'm going to talk about the next my lectures in Thursday. And some other one we can use the cost comparison also, because we can the tandem is a little bit more than that other one. These are the special, that there are some different parameters they are looking in Samsung's and LG for the just 55 inches OLED TV. So the next one, I just going to see the growth in the lighting. The first generation, we just say first generation is that first light we seen from the lamp, the oil lamp or the wax lamp we used is the candle lamps. It is used a long time ago, still some places used. So this is the first. Then the second, I think some of them is talk about Dr. Ramalingam already, but I'm just going through a little bit faster for this one. Is not much different from his teaching. So there's the next one is the junction and the halogen. Then the fluorescent lamp, which is recently it is banned in the UK now. Now we are using the LED, mainly we are using the LED lights. So the next one, we are going to try with the OLED lighting. So what is the difference is the lifetime wise is the junction is 800 and halogen, but LED is more lifetime than that OLED at the moment. And the efficiency wise also, compared to LED and OLED, with the LED is the better than OLED at the moment. And the color rendering index, it is little bit higher than that LED. But the problem we have that the first 3 of them, we losing a lot of energy. When we use that lamps, we used as a heat energy, most of them. So, but the next fluorescent lamp, which is contains mercury, that's why it is banned in UK, so we can't use it. This toxic one. And also the LED also has some toxic gases. Only when it is getting any fire in the building or anything, it can be emit. It can be you release the toxic gases if any fire, in case of fire in the building. So it can be overcome with all the problem only the OLED. So there's no heavy metal. We just using the fluorescent and phosphorescent material to make that OLED devices. So the minimum heat loss, we can even drive in that DC 10-12 volt current, we can drive these panels. So this is currently in the market, some panels. So yeah, even the panels, you can make it in curve or flexible, is OLED material. So then, well, I'm just going to see what is the difference for the OLED display and the lighting when you make some prototype device. What you have to consider that. Okay, that luminance or the brightness, we need minimum 150 to the maximum, or maximum is 1,000 candela per meters we need for the pixels for the display, and lighting panels we need 500 to 7,000 to the normal. If you want to light up your room, you need something 500 to 7,000 luminance candela per meter squared brightness needed. And the color, we need a full color. So for the display, we need the red, green, blue separately or monochrome. We need any color. But when we make lighting, we need just the white. Or if we want any decorative purpose, we need a separate color, red, green, blue. And color specification is I'm going to talk about the next slide about what is NTSC. So that more than 100% NTSC specification, it is needed for the display. But here there is no NTSC, but we need the color rendering index should be greater than 90%. And the lifetime is another one important one for that. If you drive the device at 1,000 candela per meter squared, we need at least the half lifetime, more than 5,000 hours. The maximum we need 50,000 hours to use the display. And for the lighting purpose, lighting is continuously on actually. So it means is a 0.7 lifetime. We need at least 10,000 hours to commercialize that product. Okay, then efficiency will be then luminance watt. Power efficiency, we need 10 to 100, and compared to the lighting is 10 to 180. And the backplane, we use active matrix driver or the PM driving in active matrix or the passive matrix. We want for the display purpose, but in lighting purpose, we just use some DC current to work without any drivers. Is just a simple way to can drive that lighting. We need a pixel, and there is no pixel we need. It's just a small tile, so with the panel we make it like that. And this the cost. And there are issues for because the display wise we have an issue that the cost of backplane. And here the problem is when you make a bigger pixel, bigger tiles or something, if there is a uniformity problem will become for the lighting lighting purpose. I move to the next one. So here I'm going to see what is the different NTSC. NTSC means the body is called National Television System Committee. They initially they developed 1945 design for the black and white television. They just defined the colors for the black and white. Then it's adapted to 1953 for the second standard they created for the color television. So if you want to make the color television, we need individual color pixel for the range of color coordinates we need it. But if we want to the Rec 2020, this the 2020 rules, it comes, there's a white color count. Actually, the Rec 2020 want very saturated colors for this red, green, blue, and the white. It is not only possible given by the quantum dots. It's not possible. It is not possible by the OLED. OLED can be achieved for the NTSC color coordinate system. So in our lab, we could make a prototype device for these the four of them. We could achieve the red we could achieve nearly, and the green we will achieve more than what they want for the Red 2020, and the blue is nearly same, and the color, the white a little bit away from what they needed. So we could make, it is possible with our machine, it could make these individual colors easily. So the only possible, I'm going to see the next Rec 2020. If you want to make any display, we need to use the Rec quantum dots actually. So this is the quantum dots. It's already Dr. Rama talked about it. I'm going to little bit details of these quantum dots. So the quantum dots, it's made by inorganic materials. You know that they are like that. Okay. The core actually defining the color. The color, because the size of the core will tell us the color of which color it will emit. So the core we can use cadmium selenide, cadmium sulfide, or lead selenide, like some heavy metal we can use as a core, or heavy metal free like indium phosphide sinks down for 6 months, because only the suppliers is giving the warranty for 6 months for that quantum dots. And with this shell we can make zinc selenide, zinc sulfide, like a wide band gap semiconductors can be used to make that shell for that quantum dots. And the next one, the ligand. The ligand actually helping to make the processability is easy to make processability. So defining and also is the efficiency of the quantum dots, because we can use the short ligands or the long ligands. It might change the efficiency. And also the photochemical stability also is the ligand will give it to the quantum dots. So why we need quantum dots? That's why I was talking about the REC 2020 is the narrow emission bandwidth we need. For the display purpose, we need narrow emission bandwidth, and it should be tunable emission. So this is quantum dots can be tunable emission, and also high brightness. We can get high brightness from the quantum dots compared to OLED. So you can see that actually the blue-green, which is the dark line one, and the dotted line is the OLED one. So the OLED ones is the very white color, white bandwidth one, which is the very narrow bandwidth spectrums of these colors. It is actually which we need actually. So here you can see this is the OLED can be OLED can cover this side of spectrum colors only, but QLED can go further up. All the saturated colors it will reach easily by the quantum dots, because it has a white color gamut, and also it is simple solution processability. So we can use big substrate. We can make a big size of display, but OLED we can mainly use because the small molecules there are a lot of other problems to make big, fabricate to the big substrate. It is not possible. The solution processing, it is very difficult sometimes. The solution processing can be done for the big substrate, but if we use the vacuum thermal evaporation, it's only for the short, the sizes will become smaller. And there are some other problem. The thickness evenness also is the problem for the vacuum thermal evaporation. Okay, then I will move. So the flexible display application also it is possible by these quantum dots. Right, now is the current status. So there are some European health safety restriction we have. So the cadmium-based one is not possible to use for any commercial product. Only the cadmium-free, like indium phosphide, zinc selenide type of quantum dots can be used to make display or lighting purpose. So there are external quantum efficiency that the cadmium-based. I think probably is more than it's about more than 25 we achieved at the moment. It is in worldwide achieved, but cadmium free one is around 2021 for the red one, and the green one, this is more than 25 cadmium based one achieved, but cadmium free one is under 15 still. The blue one, cadmium based, is 18, and cadmium free one we have a problem. That's only less than 10% external quantum efficiency is achieved. The lifetime is the main problem for the cadmium free one, which is the heavy metal free one, as because we don't have any lifetime for the green or blue. Still, it is not possible to use for any display or lighting purpose still. Now that the QD technology, the modes of operation, what's the mode? There are two modes of operation we are looking at that QD technology. One is the photoactive QD technology. Other one is optoelectronic QD device technology. So photoluminescence, which is the photoactive QD technology, means just the photoluminescence. Photoluminescence means just you passing the light and you getting the if it is the red QD, you will get a red emission. It's like a color filter. It's just blue color. Blue color lighting. The backlight is blue. Then you can get some red. Use the quantum dots. You can use the red. There is no electroluminescence. Electroluminescence is just that photoluminescence. It's like a filter we are using at the moment. So this is mostly it is used at the moment for the LCD TV to make QLED TV. Yeah, but if you take optoelectronic QD device technology, which we are looking forward, that's electroluminescence. Electroluminescence means you just passing the electricity through the quantum dots, then it will emit. That it actually that's self-emitting. So that the whole and protons is exciting here. I think Ram already talked about. I'm going to talk more details on Thursday, but this is happening. There's holes and electrons meet here. Then they are emitting the which photoluminescent. Then it will emit that color. So there are some electricity is applying, then that luminescence is self-emitting that quantum dots. It is actually we are using for light-emitting diodes and field effect transistors. This one actually this here in photoelectric also. Photoelectric means it's like you're getting the sunlight or any lights through that. Then there are current is creating by that dots, the quantum dots. So yeah, this is the solar cell or photovoltaic devices. So this purpose we are using these two. So this is actually it is at the moment in the research is not commercialized yet. It's just in that initial stage at the moment because it is not reached the needed efficiency or lifetime yet. So we just looking first one is the photoluminescent commercial product in the time frame. It is actually really the first photoluminescent quantum dots product came in 2002, which is the Q dot probes for the medical purpose, but still they are using. And the next one, 2008, that they made the Evident Technologies made Christmas tree lights. So that is the first lighting made by this quantum dot. But this is just the photoluminescence lighting. And the same year or the next year, that Nexus lighting QD vision, Nexus lighting with QD vision quantum dots they used and make that QD LED lamp. They just do the quantum light optic. It's like a color filter. They use the color filter front of the LED. They stick front of the LED lights and made the lamp, QD LED lamp. They made it in 2010. And the first display, the first television display, it came with Sony and the QD Vision collaboration. They just made with the color filter also, this color IQ optic filter, which is made by QD Vision. They used and make the first television with the came out in 2013 to 16, but the lifetime is not very good, but still they made it on that time. And the next move, that Nanosys, they made some QD enhanced film. They use within the barrier layer. They make they they use this quantum dot on the barrier layer, and then they make the actually they made it like that. That's they just fabricate that the quantum dots, and they encapsulated that film. They used for this one to make. They used this one in the LCD television. So then it is in 2019, which is, I think, currently they are using for their LCD television, the QD LED television. So this is the film is made on the glass. And the next one in 2018, the quantum dots being used for the greenhouse films, that the UBQD made luminescent greenhouse films. So this film actually, they used the copper indium sulfide film they used, and this for the greenhouse purpose, they use it for this quantum dot photoluminescent product. And then now, I mean, 2019, the Osram made some lights. That light actually, that lighting downlight application, it's like a big panel. They just use it with the LED for this color filter, the quantum dot color filter they used to make these lights. These are the photoluminescent product from the quantum dots. So this the photoluminescent. I mean that color filter. How does it they encapsulate it? So they used the barrier film. So barrier film being encapsulated using the adhesive, then UV curing that film like this. So this is called macro encapsulated QDs. So macro encapsulated QDs can be in barrier film or the glass. They coat the quantum dots. Then they encapsulate it. Then the nano encapsulated means they just individual quantum dots like that to protect the shell. Because that why we need to protect the quantum dots? It is easy to die by that oxygen and water. We need to protect from the oxygen and water to live. I mean that quantum is to alive. Otherwise, quantum dot will be won't longer time. It won't be there. I mean that the purpose won't be can't be done by without when the oxygen, water, or the moisture will be affected. The quantum dots easily, then it won't work as we need it. Then the quantum dot technology for the solid light is just for the solid lighting. This is from 2009 to now. The first, the LED that just the cool. So we just compare the power efficiency and the color quality. So the first in 2009 state of art, but it was that cool white LEDs gave best efficiency, but color quality is not very good. When they use the quantum, quantum dots filters, that it will give with the best power efficiency. Also, the color quality is given. It is they could get easily by using this color filter, quantum dots color filter. It is actually satisfy both power efficiency and the color quality. So there are some other ones. The fluorescence, it was some power efficiency, but the color quality is not very good. And also the warm white LEDs, which is the more red emission LEDs, they are also that 50% power efficiency, and the color quality was, and the condition lamp was only both the best color quality, but power efficiency was very low. So now 2019, in 2019, the Osram used this color filter actually that make the efficiency is 173 luminance per watt, and 3000 the color temperature. It was 3000. This is the warm. The warm white they could make it easily, by using this color filter. So now, yeah, the color temperature they could make it 2,700 to 6,000 using by this photoluminescence of the quantum dots. Now, we just look at the commercial displays. It's 2013. This is the first display they made it. So what they have used, there are nanosys and nanosys quantum dot and 3M barrier layer. The producers, they collaborated and make the quantum dot enhanced film. They made that the Amazon Kindle, the 7 inches Amazon Kindle, made it by using this color filter. And the same time, the same year, the QD Vision with Sony, they use the color IQ optic with the glass. They just use the television to make that LCD television, use this color filter to make this QD LED television at that time. So now there are many other people, 2021, there are Samsung, LG, HP, VCO, TCL, Hisense, many of these manufacturers making QLED, QD LED television with using this enhanced film. Right. So now we will see what is the difference. The QD's display, what actually giving us at the moment is because when the LCD TV using the POSPA color filter, they could actually get only 16 million colors. When they use the quantum dots filter, they will get 1 billion colors. So this is 64 more color than that, 64 times more color than that normal LCD TV by using that quantum dot filter. So the backlight, both they use the LED blue lights, but they could achieve the bright and I think the saturated color and also the energy efficiency by using this quantum dot they achieved. So there are this is just the blue. They are normal blue blue LED, and this they used in the liquid crystal display. So when they use it, they can make it more colors by this POSPA. They can make it like this, but when they use the quantum dot filter, they will move to narrow. I mean that the full width half maximum is become 25 nanometer. They can easily to tune from 50 to 25 by using this quantum dots filter to the display. Okay, here there are much to say about it. This is here I'm just going to talk about something, that the different how the filter is used. This is, I don't think so it is anything important. So I just moved to here there are different TCLs, which is that Chinese manufacturers making their LCD and the quantum dots, how they moved from there using the backlight OLED and the QLED and the macro OLED. And this I'm going to see in the next slides. Okay. So this is next slides. Okay. This is one actually that what's happening with the QD LCD TV and that OLED TV. So actually the QD LCD TV very mature product, and still they are leading the blue one. They are the market leaders because the cost of producing is less compared to OLED TV, and also the color saturated colors you can get easily from the QD LCD TV, which is they are using the quantum dots enhanced film only, is photoluminescence quantum dots being product. Okay, this is the commercial product which this backlight is the blue backlight, and the LCD TV and the quantum QD enhanced filter is used. This is the commercial product now at the moment, currently. So the next one they are looking for, they are going to use the OLED backlights. Here this is the LED backlight. They are going to use the OLED backlight. This is the OLED unit. They are going to OLED backlight. Then these filters, this blue, green, red quantum filter they're going to use and make the next generation of display. And also this one also the soon they are going to be using the macro LED. Macro LED also they are going to use it. Then using the enhanced film. So this is the current research on, current product. They make the product on the research side. They are happy to launch in the market soon. These are the product using, but the backlight only going to different from LED backlight, and this is going to be OLED. Then here the macro OLED light backlight they are going to use, but still same filters, quantum dot color filters will be used to make that display. The next one, okay, this is just the photoluminescence. So which up to 23 we can't expect electroluminescence QD because of the lifetime, and that the cost of manufacturing is very high still. So these are, I have already talked about this. These are the things we are going to see until 23. Then most probably from up to 25, that quantum dots itself emit, and it will make more saturated colors. Displays will be available, and these are another product they are expecting, the QD lasers. It will be in the market after 2030 for that for the display wise they will use it. Okay, this is some summary. I'm going to see it again for what the Samsung. So what they are using, that currently they are using the LCD with the QD film or QD color film conversion filter. They are using enhanced film or QD film. They are using QD conversion filter they are using to make here. What's actually happening here? They are using QLED TV mobile. They are using for this technique, and they are using for this mobile phone. They are using these ones. So actually the color camera BT 2020 is the REC 2020. Is they could achieve more than 90% for this, but in OLED TV, this OLED TV on its own, and this using that white OLED with the color filter. This is OLED with quantum dot color filter, which actually LG is mostly trying these ones. So this is using for just the mobile, and these are the display they are using here. But they could achieve only more than 80% of REC 2020 colors in the mobile, and here the display they couldn't get anything for that. Even when they use the quantum dot color filter, they could greater than 80%. So this is what we are looking for. But if we use quantum dot electroluminescence, the quantum dots itself emitting, then we can achieve greater than 90%. So that's a large area. It is possible because we just using the filter for this, but OLED wise, OLED itself, we can't use it because OLED is not possible to make very big, we can't evaporate to the big substrate. So it is not possible to make a large area by using the OLED technology itself. So if we use the color filter, it is possible then can be done for that, and it is definitely we can use, because it's mainly we are going to use the solution processing, printing, or just speed coding can be is done. Even thickness of film we can easily to make the lifetime, but LCD device is high, but OLED still low, but still we are expecting we can make high lifetime and high luminescence from the QD-EL. So saturated colors, because we are using QD color filter, we can easily, but here contrast ratio, OLED TV is more contrast ratio, we can get it, but still saturate is not possible. But this we can, if we make the devices with QD-EL, it is possible saturated colors and the high contrast ratio. So this is just that I'm repeating this one. This is more clearly it is saying about why this QD enhanced film used in the LCD TV, and how is it and how is the filter is used, the blue light, and using this filter, how we getting the different colors from the filter. This is the technology currently used for that. It's very they need many frames. I think like a polarizer, color filter, liquid crystal, TFT glass for this, and this the quantum dots enhanced film being used. This is, and the back cover and the display. So this is a very long. We need. I mean, there are many frames being used to make this quantum dot enhanced film technology, which is for the LCD technology. It is used for the LCD. The next one, they are looking for the backlight. They can use blue OLED or macro OLED. Then they can easily to reduce that number of frames to make. This is the QD conversion. Color conversion filter for this macro LED or blue OLED backlight. If we use it, we can reduce further. The next one, then the final one they are expecting from emitting QD-EL, and this is the display. You can the viewing point here. So this is, we will see very thin. If it is possible, we can get it soon, this one. So this is some lighting what we have done at Brunel. So we use the quantum dot. There are 3 prime colors. We need the 3 stacks. I'm going to talk about this structure, about this the lighting panel. So later, but here we use zinc oxide as a solution process, and quantum dots, red quantum dots we used as a spin coating fabrication, and these all are we used vacuum thermally evaporated, and we could make a very good white spectrum. The color coordinate is 0.334 This is at 830 candela per meter squared. This is the panel. So we could play. Okay, this is the it's very bright. Even that outside our room light is on, still you can see the device we made 10 centimeter at Brunel. And this is some displays where we went to that normal conference, that the demos we have seen. I just and also my boss, Professor PK, is here. So That's all from me. Thank you very much. You're giving the chance to talk about it. Thank you.
Yeah, thank you, Professor, for giving very detailed and chronological order of the evaluation of QLEDs and other LED displays.
Thank you.
Yeah, thank you so much, and very nice presentation and very detailed, more informative presentation.
But I am not a teacher to teaching because I can only say my experience, what I have achieved, and also what I learned during my, because I don't teach to the student actually, so I might sharing
Yeah,
my knowledge. That's all, yeah,
yeah,
Rama.
definitely that experience speaks. The experience speaks rather than the conventional.
Thank you, thank you.
Yeah, so thank you so much for a wonderful presentation. And now the session goes for open discussion. So, participants, faculty members, scholars, if you have any discussion or any queries, doubts, you may unmute and directly interact with Dr. Kumaraveli. So, participants, if you have any queries, please you can unmute and directly interact with us. No queries? So, there is a question from YouTube. No. Yeah, so, sir, Kumaraveli sir.
Yeah, thank you.
Yeah, there is a question from Dr. Bhaskaran sir.
Yeah.
The question is, what is the strategy to increase color quality and power efficiency together? What is
For
the
the Q,
strategy to increase? What is the strategy to increase color quality and power efficiency together?
yeah, color quality, we have a problem because color quality is mainly from the quantum dots itself. Yeah, if the quantum dots have a good spectral wavelength, it's like, if we, let's take about red. If we take about red between 630 to 640 nanometer, we could get a good color quality. When we do the photoluminescence PL, when we run the PL of the solution, we know the color quality. If it is less than 630, then okay, say 630 nanometer, if we get it from the photoluminescence, we could increase by changing the ETL and the whole transporting layer. We can move little bit, to the blue side of, move to it's using that. It's depending on the core transporting site. We can improve to good color. If it is moved to 630 to 640, the color quality will be improved easily. So it's all dependence of what ETL we are using. And the next question is power efficiency. Power efficiency, we need to reduce the layers of the quantum dots. The dots means if we take red, it might be 6 nanometer radius. 6 nanometer radius of dots. Yeah. So if we use 3 layers, it's going to be 18 nanometer, 18 to 20 nanometer. So if you minimum, we need something 3 layers. If we make thicker, if it goes 30, 40, then we can get a good color, but the efficiency will go down because the voltage, the current we need more, the voltage will be increased, the power efficiency also will be decreased. So we need to compromise all because the thickness issue there and plus the quality of the quantum dots. This can play with if we have a good quantum dots, we can get good color, and we can play with the other layers to improve the power efficiency.
Yes, sir. Yes, sir. Thank
That
you, sir. So yeah,
Anything else?
Professor Bhaskaran sir, you can directly interact with the Kumaravel sir.
Thank you, sir. Nice
Hello. Yeah.
presentation. I have
Thank
one
you.
more question.
Yeah, sure.
How can we handle quantum dots for QD LED? Won't we get agglomerated because the quantum dots are very fine particles? And what is the effect of agglomeration of quantum dots versus color quality?
Because quantum dots, if you have in room temperature, it is not going to accumulate that easily because it is the lifetime for 6 months. Because I'm not making any quantum dots. The first, I'm not a chemist. I'm just making the devices. So I'm going to talk about from my view point of view. It is, if we keep the quantum dots in the room temperature means is 23 degrees or between 20 to 23 degrees is normally our suppliers recommended to us. So we keep it like that. Then we can use it for 6 months. And also we use, if they give something 100 milligram per milliliter, then we dilute it to 5 milligram per milliliter. We use normally 5 milligram per milliliter. If we want to increase the color quality, then we can increase to 7 or 10, maximum 10 milligram per milliliter. So, and the solvent, what they recommended, I use normally. We normally use mostly toluene or octane for this red quantum dot. So the cadmium free actually we are using because we banned use the cadmium based one. So we mainly use the cadmium free and indium phosphide base for red and green. And cadmium, zinc selenide we use for blue. So this mostly we use toluene or octane. So if we use these solvents, we didn't have any problem, but we normally dilute when we need it. Otherwise, we will keep always as it is, how suppliers supply to us. So we don't need to mix. When we need for a week, how many milliliter we need, we just make from that concentrated one to from the concentrated to that from that suppliers quantum dots. Then we dilute it to what we need it. Is any help you?
Thank you, sir. Yes, understood. Thank you.
Yeah, because that the depends that the concentration is the important thing. So we don't need a very concentrated quantum dots because quantum dots, when they buy it, they normally give 25 milligram per milliliter concentration or 100 milligram per milliliter concentration. Then we just use the same solvent to dilute that. If it take 1 milligram from their solution, 1 milliliter, that's 100 milligrams there. So if we want 5 milligram per milliliter, we need to add 19 milliliter of that same solvent to make 5 milligram per milliliter. That's the way we used, and we used that for a week only. But before we used, we always shake the bottle, and then we use it. We use mainly for spin coating. We're not using any printing at the moment. Yeah.
Okay, thank you.
Thank you.
So nice technical presentation, sir. I have one doubt.
Yeah.
Sir, how could measure the efficiency lifetimes? Lifetime efficiency of LEDs.
Are you joining with us on Thursday? I'm going to give a detailed explanation for this, how we are doing the characterization for these devices. Then you will learn, because I'm going to talk about on Thursday that 2-hour slot about making device and all this detailed. If you join that day, I can easily to explain, because it's a little bit, I need to go detailed explain, otherwise you won't understand. I mean, you might not understand. So if you join on Thursday,
Sure, sir.
I'm going to talk about this one, please. Yeah. Thank you. Any questions from anybody?
Yeah, sir, thank you. There is another question.
Yeah.
By Ramanathan. So the
Hello,
binding of,
Raman.
yeah, I think, yeah, Ramanathan. Hello, Ramanathan. Yeah, so he raised the question in the chat box. So
Yeah.
the binding of organic compounds with the core shell, the binding of organic compound with the core shell, without core shell nanomaterial, the power conversion is increase or decrease.
Course is a quant, which I didn't understand the question because I am not a chemist, Rama.
Yes,
If
fine,
you,
fine, yeah, understand. Now
yeah,
the question is if you are making a core shell type of material, if you're making a core shell, whether the power efficiency increase,
yeah.
or if you without core shell, whether the power efficiency is
I didn't.
decrease.
Excuse
So
me,
that's
Rama.
what.
You know the
Yeah,
course. What is
yeah, I
meaning of the
understand.
course? What is
Yeah,
the meaning of that? Because I have no idea that.
yeah, I
I don't
understand
want to
that
say anything
if you
wrong.
are making a core and the shell,
Core and the cell. Okay, core
yes,
and the cell. Oh, yeah.
if you making core and shell, that definitely the power efficiency is increased. Am I right?
Yeah, that's right. If you increase the core, that's a color dependent. So you can't increase the core, but
Yeah,
increase the cell thickness.
shell thickness.
The
Yes.
publications are saying that definitely you can improve the power efficiency.
Yes, so if we increase the shell thickness, then there is a possibility of increasing the power efficiency
Power efficiency and the stability also,
and the
the
stability,
device
etc.
stability, the
Okay.
lifetime. And if you put another cell, we can use 3 cells even. Take cadmium selenide, zinc sulfide and zinc selenide. If you use 2 cells, you can improve the stability and power efficiency also.
Okay. Okay.
So this is all, I am only making device. I am not making quantum dots. Yeah, that's
Yes.
a
Yes. I
chemist.
understand.
Yeah,
Yeah.
yeah. But I know this is can be done. If we use more cells or thicker cells, you can improve the power efficiency. But there will be a breaking point there. You can't increase as much as you want, but it
Mhm.
has to be stopped somewhere. Yeah.
Okay. Thank you. Kirti, you want to ask any question? Please unmute and you can interact. I think she's not okay. Sir, I have a question that are you doing a project in this LG company for making of device?
No, we used to make for Samsung, but at the moment we are doing project for signage using the quantum dots, cadmium-free quantum dots. We making signage for our the UK company. They just making the big signage on the roadside signage. They wanted to use at least one color for their signage. They're using the LED now, but they want to put quantum dots instead of LED. Yeah, so that's we try to do now at the moment.
Okay, okay. Sir, another question is, this is my question actually. So as you
Yeah.
said that in this presentation, the quantum dot is stable for 6 months. Actually, we tested also it is 6 months, 3 to 6 months. Okay, fine. So
Okay.
if that is the condition, if you make the device, then the stability is also
No.
6 months, no? Or
No. That's after you make the device that your quantum dot structure will be changed, isn't it? They are protected by other layers. It is actually they are in the different. I mean that is going to be changed because it is in the dots itself, and with the solvent might be different from the going to make a film. The film, I think, film lifetime is more than 6 months. Yeah, that is different. This is with the solution only the lifetime 6 months. But when you make the film, after you make the film from the solution, it
okay,
will depend on other layers also. But it is more than
okay.
6 months, definitely. Yeah.
So in generally, how long you will give the stability for if you are making a device?
device, we make a device with different structure. Structure means, the thickness of the layers and different material we use for the layers. So then the lifetime will change for that. We can't say this is the lifetime, but we can say for this structure, it can go this lifetime. For our prototype, because prototype devices different from the normal manufacturing condition. Manufacturing condition is more reliable. Our prototype is not more reliable. We just sometimes we handling air, but they will handle everything inside the nitrogen environment or they properly
in that atmosphere. Okay. Yeah, fine. Yeah, fine, sir. Thank you. Yeah.
Thank you very much.
Thank you so much. So I think it's almost we are running out of the time. So I would like to call upon Dr. Bhaskaran sir for giving vote of thanks to Professor Kumaravel sir.
Thank you.
Yeah, Bhaskaran sir, are you online?
Yes, sir.
Yeah, can you give a vote of thanks to Professor Kumaravel sir?
Yeah, sure, sir. Thank you very much. Actually, Dr. Kumaravel sir gave a wonderful presentation, and he explained about the OLED, the difference between QD-LED, and about the future devices for 2022 to 2030, what we are going to have in future. He actually bring the future into our screen. So it's a very wonderful presentation, sir.
Thank you very much. Thank you very much for giving the chance to talk about my knowledge from Rama and Alagappa University.
Thank you very much, sir. You cleared all the doubts in a very detailed manner. Thank you very much.
Thank you.
Have a wonderful day. Thank you.
And you too. Yeah, thank you.
Yeah. Thank you, sir, Kumaravel sir, and thank you, Dr. Bhaskaran sir, and I also thank all the participants who are actively engaging in this forum. So each and every one of you, I thank so much for joining us. And tomorrow we'll have the same schedule, so there is no change in the schedule. So we'll start tomorrow. The lectures will be taken by Professor Abhishek Lahari for 2 hours lecture. So in the Indian time, it starts from afternoon 2 o'clock to 4 o'clock. So 2 to 3 one lecture, and 3 to 4 another lecture. So 2 lectures, which is going to be handled by Professor Abhishek Lahari, Brunel, and he is going to deliver the talk on bottom up and top down process of material fabrications, and the mechanical exploration and chemical explorations. So in detailed manner, he is going to give his presentation by tomorrow. So on behalf of organizing committee, I request to join hall by tomorrow at 2 p.m. of Indian time. So thank you so much.
Thank you. Bye-bye.
Yeah, the link will be the same link will be used for entire 5 days program. So no other change in the Google meeting link. So the link will be the same for entire course. So you can join the same link and enjoy the course. So thank you so much. Kumaravel sir, Bhaskaran sir, thank you.
Thank you, Rama.
Thank you.
Thank you, sir. Thank you so much. So we'll end up this session, today's session. So we'll join tomorrow. So thank you all. Thank you, participants.